maybe by Monday or so. Okay, and yeah, so that was what I wanted to tell you. So then, now let's maybe begin our discussion. And so as
Sir,
we saw in, yeah,
sir, you want to know 1 hour slot is on which day?
yes, any day is fine actually. Any day, Tuesday, Wednesday, Thursday,
So on
during the week,
Thursday
1 hour.
there are from 10
Yeah,
to
just think of
1
it.
there are no classes on Thursday.
10 to 1 morning.
Yes,
Sir,
sir.
basically on Thursday, no morning classes there. Only afternoon classes are there.
Yes, sir. After the line, there are
Okay, so maybe
classes.
Thursday 12 to 1 we can reschedule if needed, although that will be needed only once or twice. Yeah, but yeah, thank you for letting me know. But yeah, just think about think about this more, because there might be some more things that might be scheduled during the week, because there might be some tutorials, some other your hobbies or some other engagements can be there. So you can let me know about it maybe by next week, finally. Okay, and now let's maybe start our discussion of ECN 101. All of you are requested to mute your mics, and whenever you have any question, you can unmute and ask. So essentially, in electronics, in ECE, we study electronic devices, we study transistors, we study diodes, junctions, and we study systems made out of those devices. Then the second most important part of electronics of our department is how various systems communicate with each other. And that's essentially the communication engineering. We in our last class yesterday, we saw that internet is one of the greatest example of a communication system that exists or that has ever existed in the world. Uh, so you might be aware that that the devices are practically the devices are made are not used standalone. Practically, we do not use a single transistor, or we do not use individual transistors. We use integrated circuits, and as the name suggests, integrated circuits or ICs are when we integrate a whole bunch of devices on a single chip, and that chip gives us a certain functionality that is known as the integrated circuits. And in fact, the invention of integrated circuits was one of the biggest landmark in the development of electronics and communication engineering. Okay, so that's why it is important to know. Just to sort of show you the progress of our discipline, uh, this is how it looks like in this plot. So on the x-axis we have the years 1970s to 2010, and this can be further extended to 2020 or 21 even. And as you can see on the left side of y-axis, uh, this is the cost per transistor. On the right side y-axis, we have the number of transistors per unit area of the chip. So per centimeter square of the chip, 1 by 1 centimeter by 1 centimeter of an integrated circuits. And as you can see, the number of transistors on the same area per unit area of the chip is consistently increasing. And as a result of that, or along with that, the cost per transistor is consistently reducing since last now 50 years almost, since the invention of the integrated circuits. And this is termed as Moore's law essentially. So Moore's law says that number of transistors on a chip on a unit area of the chip would be double every 18 to 24 months. So around every 2 years, number of transistors on the same area of the chip would double. And so this principle, or this phenomenological principle, is known as the Moore's law. This is not a fundamental law of nature. This is more sort of a trend. This is a trend in electronics and communication engineering. especially in electronic devices. And this is what uh, our discipline has been following since last 50 years, since the invention of the ICs. But there is a catch here in 2020, since last 1 or 2 years, the Moore's law is no longer actually being followed. So since, as you might be aware, that nowadays the length of the transistors is nowadays around 5 nanometer, or even 7 nanometer, 8 nanometer is quite common. But the 5 nanometer, even 3 nanometer technology is being used. So the length of transistor is shrinking at extremely fast pace, and there is a limit up to which we can go in making these transistors small. Okay, so now that
So one
limit is approaching, because yeah,
so
there
my
seems
question
to
is
be a
that
question.
sir, that the lesser the area, that like 6 nanometer, 5 nanometer, more efficient is the chipset. So sir, why is that called?
Why is that sort of? Sorry, what did
So
you say?
because
Why is that?
like the 9 nanometer chip and then the 8 nanometer, then 6 nanometer. So sir, as the nanometer decreases, sir, the
Yeah,
length decreases, sir, the chipset becomes more efficient.
chipset becomes more efficient. What do you mean by efficient?
Sir, I have recently purchased one mobile. So, sir, in that the
Uh-huh.
processor it took was like 6 nanometer, 7 nanometer, and
Yeah.
I researched about it. So I got to know about the lesser that the nanometer is, like 5 nanometer or 6 nanometer. The best chipset like are having less nanometers, less length.
Okay, yeah. So yeah, that I get your question. So when we understand, or when we characterize the performance of a chip or performance of a device, generally there are multiple factors that we need to account for. One is the power dissipation, how much power that chip is dissipating. Second is the speed. Speed means how fast that chip can perform operations. That is given by the number of operations per unit per second, per unit time. So generally, as the device is shrinking, we can put more transistors, and the number of operations that the chip can perform is increasing, because we have more transistors. We have more freedom um, to do things on the chip. But at the same time, this second factor, the power dissipation, this becomes a challenge. So till now, we are sort of managing this. We are enhancing the number of operations per second, and we are also managing the power dissipation, so that chips are not uh, chips are not heated for because once a current is flown through the transistor, it dissipates heat, and if there are lots of transistors in a chip, lots of transistors will be emitting heat, and that will increase the temperature of the chip. That might reduce the performance of the chip, because the transistors may not be functioning as they should function at room temperature. So there is always this trade-off between the speed and the power dissipation, and the delay in uh, the delay that the electron takes to go from one transistor to another transistor. So till now we are able to manage this. Till now the performance is consistently increasing, but now it seems that we are hitting the ceiling. We are hitting the limit. It is becoming more and more difficult to further reduce the size of the transistor, because fabricating a transistor which is less than 5 nanometer in itself is a challenge. As you are aware that atomic dimension is a few angstroms, basically tens of angstroms typically. So if the distance between two silicon atoms is 10 angstrom, in 5 nanometer channel, there will be only 50 silicon atoms in the channel. So we are already approaching the atomic dimensions. There are only few atoms in the device, in the transistors nowadays. And when we go to those limits, fabrication becomes extremely difficult, because it is extremely difficult to manipulate individual atoms or atomic layers. So things are becoming difficult, and that's why this Moore's law is now, people are saying that the Moore's law is now saturating in a way.
Sorry to interrupt, sir.
Yeah.
Sir, can you please explain what you explained in the beginning of the class? I was not able to join.
So in the beginning of the class, I quickly reviewed what we discussed in our last class. We discussed that in our department, generally we study electronic devices, we study circuits made out of devices, and uh, then we study about the communication between various devices. Then we discussed this slide in which I showed you the Moore's law, or the trend that the electronics industry is following since last 50 years. And the trend is that the cost per transistor is consistently reducing, and the number of transistors per unit area of the chip is consistently increasing. And this trend is termed as Moore's law. But this Moore's law is now getting saturated, because now the device size is around 5 to 8 nanometers, and it is extremely difficult to fabricate smaller devices than this dimension, because now there are only few atoms, and even if there is a small mismatch between two atomic layers, it results in uh, huge dissipation. It results in imperfections in the device, and the device performance goes down. So that is essentially the state of the art in electronics industry. Okay, any other question that you might have? So this is typically the layout of a chip. Uh, if you magnify this, you will see individual transistors, and this is a very small area of the chip. And so essentially nowadays we cannot uh, see one transistor with our eyes without a microscope. That is, nowadays there are billions of transistors in 1 centimeter square of the chip area. Okay, so many billions of transistors. So transistor has essentially become among the most numerous things in this universe, on the earth nowadays. Okay, so this is the top view of the electronics industry. This is what is currently happening. And now, so using these chips, we make devices, we make mobile phones, laptops, other devices, and then we try to set up communication between various such devices. But essentially, at the bottom of it, this is the game of electrons. If we can sort of say that all electronics engineering is the game of electrons. Essentially, what we are doing is we are manipulating electron flow through the transistors. Or even electromagnetic waves come from the vibrating electrons, and even in communication, we use electrons. In devices, we try to manipulate and control electrons. So the electronics industry, electronics engineering is essentially the game of electrons. And if you need to, or if we need to, or if we go to the root of all electronics engineering, it is all about understanding the electrons and controlling the electrons. Okay. And electron is something that I guess all of you know. So can any one of you tell me what is an electron, or how do you define an electron?
Sir, it's a
Subatomic particle present in an atom.
It's a subatomic particle present in the atom. Anybody else has an alternative definition of it?
It's a negatively charged subatomic particle.
Yeah, what do you mean by subatomic particle?
Sir, part of atom.
So that is present within the atom.
Okay, anything else about electrons? Is that the way to sort of define the electron completely?
Sir, it is a subatomic part of it is a part of an atom having negative charge, and it is the least amount of charge that something can have.
Okay. Anyone
Subatomic
else?
particle possessing dual nature.
Yeah, so essentially, yeah, you're right. It is not a particle, first of all. It is definitely subatomic entity. It is present in the atom. It is one of the constituents of the atoms. Okay. So in a more formal way, it is said that it is one of the fundamental particles or one of the fundamental entities that exist in this universe. Okay, or it is one of the fundamental manifestations of the energy. In other terms, if we think in terms of in string theory or energy vibrations. So electron is something which is not a particle. Do you agree?
Yes, sir.
Then
Yes,
is
sir.
it a wave
Right.
or is it a wave or is it something else?
Is it a
It's sort of both
So dual
because
nature.
It has
The
dual.
dual nature.
all the subatomic particles
Dual
have
nature.
weight.
Sir, it is a wave particle duality.
Yes, it follows wave particle duality, and in a way it is said to be said to possess dual nature, and by dual nature people or everybody mean that electron uh, can exist both as a particle and both as as a wave, but essentially it is neither a particle nor a wave. It is something else. It exhibits the property of both of them. Okay. uh, have anybody sort of actually seen an electron?
No, sir.
now, sir?
No, sir.
No,
No,
sir.
No,
sir.
sir.
No,
Is
sir.
it even possible to observe an electron, in your opinion? What do you think?
No, sir.
No.
No, sir.
No,
Sir,
sir.
exact
Why is
location
that the
cannot be
case?
defined.
No, sir.
Uncertainty to
No.
uncertainty.
Heisenberg principle.
Yes. So electron is something which cannot be defined properly. It is neither a particle nor a wave. It is nothing that we know of. You agree with this? It has never been actually seen by human beings. So it is everything that we don't know. But still, all electronics engineering is based on electrons. So does that sound a paradox to you or not?
Yes, sir. Yes, sir.
Yes, sir.
No, actually, it's not a paradox actually. So electron or any other fundamental particles, elementary particles, we have indirect.
Sir, you are on mute.
Sir, you are not audible.
Yeah, sorry. So yeah, so it is actually not a paradox. It is uh, or any fundamental particle, any elementary particle is not is we don't know most of the things about them. We haven't seen them, but we have mathematical models through which we can understand them. We have very elegant maths to understand them. We have very grand experiments through which we can control them. Although we do not understand about the nature fully, but still we are able to do quite a lot of things with with nature. We are able to control most of the elementary or many elementary particles, and electron is one such example which human beings have understood, controlled, and used as well in technology. Most of the technologies, uh, most of our existing technologies, especially electronics technologies, are based on controlling the electrons. Okay, so even if we do not understand this fully, even if we would not be able to understand this fully, but even then we have very good maths. We have quantum mechanics, which models the electron fairly well, and that's how we do electronics, or that's essentially the starting point of the electronics and communication engineering. Okay, so at the foundation of electronics engineering lies the electron. Although all electronics engineers need not know about electrons, one can assume that something like electron or something like a fundamental particle exists, and based on that understanding, uh, one can do a lot of things. One can also understand devices, one can understand communication between the devices. But if you want to understand fundamentally, if you want to understand things from the root, you need to understand the foundation of the field. And that's why having a good understanding of physics and maths is very important in electronics, in ECE. Although one can do ECE BTech without having a very sound understanding of physics and maths, but in my opinion, that understanding is hollow. That is just remembering things. That is not the real understanding of the field. Okay, and that's why I advised you to uh, go back to physics and maths in your free time. So this is essentially the introduction of the field. This is where it is going, where it has gone, and nowadays, as we have seen that Moore's law is saturating, and it is no longer possible to make devices which are smaller than. It is extremely difficult. It is not that it is no longer possible, but it is very difficult to make devices even smaller, and that's why. Uh, New kind of devices are now being discovered or thought about. So that's why this people are moving away from conventional transistor based technology. People are now looking into quantum dot based systems, molecules, organic molecules based systems, organic electronics. So there are many streams that have opened up after uh, uh, in recent years, because the difficulty in minimizing devices is increasing. Okay, and that is also the reason. So apart from the difficulty in our industry in electronics engineering, you might also have heard about it, that fabricating a chip, purifying silicon and making a pure silicon wafer, it is extremely expensive exercise. You might have heard about this, that it needs billions of dollars of investment to set up an electronics fabrication facility, and that is apart from billions of years in setting it up, it has also extremely high running cost. It needs extremely pure water, it needs uninterrupted power supply. Even small fluctuations can make huge difference, and so it needs huge infrastructure, huge investment, and that's when this electronics fabrication, electronics foundry can be established, and that is exactly the reason that there are very few electronic foundries uh, in the world. And nowadays, the biggest one is in Taiwan, that is known as TSMC, Taiwan Semiconductor Manufacturing Corporation. So that is the biggest chip manufacturer, biggest IC and devices manufacturer in the world. India also used to have a fabrication facility. It was actually Indian fabrication facility was started before TSMC. It was started in 80s, as far as I remember. and it went very well. It started very well. It was started in Chandigarh, SCL Mohali, in fact. It was called SCL Chandigarh, Semiconductor Corporation, something like this, SCL. Nowadays, uh, uh, it is there even now. But what happened was in late 1980s, it was rapidly progressing. It was getting established. Government was also supporting it. Funding was good. Technology. It was actually our scientists were very good in that foundry. But late 1980s, a fire broke out in SCL Mohali, and that essentially, uh, I would say, devastated that facility. So, and it is not clear even now why that fire broke out. It is extremely, uh, nobody knows the reason what happened there. Okay, but that was a huge setback for India in electronics industry. After that, India could not recover. We do not have our own foundry. We do not manufacture devices and chips. SCL Chandigarh tried to recover. It still makes some devices, but those devices are very old. It is nowhere uh, close to the modern transistors that the SCL makes. There is a question from Aniket sir, is small transistor more better than bigger one? Yeah, so the small transistor can be, so when the transistor is small, we can put more number of transistors in the same area, and that way we can perform more number of operations in the same size of the device, in the same device. So that way a small transistor is better than the bigger one. But a small transistor, uh, the 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 size reduction comes with a always comes with some challenges. As the transistor size is reduced, there are new challenges that come up, and those challenges are known as small channel effects that you would see in your coming courses. But practically, we try to make a transistor as small as possible without changing the functionality of the transistor, so that we can put more transistors and we can perform more number of operations in the same area of the chip. Okay. Any other question that you might have? Yeah, if not, so as we have
Sir,
seen that, yeah,
I was just asking that as number of transistors go up, price per transistors go down. So
yes.
if Moore's law is reaching saturation, so is the second part of it also reaching a saturation that we are not able to control the price per transistor?
Yes, it is. So yeah, that's what I also meant, because now it is becoming more difficult to make a small transistor. So the cost is increasing because we need more precise machinery. We need to do more precise manufacturing. So the cost is also increasing. So that way,
So,
we are saying that the Moore's law is getting saturated, and
got
that's why
it.
there is a push on making push for alternatives of transistors. Okay, so what we can essentially see is that it is about understanding the nature of electrons and controlling the electrons, our discipline. Uh, in other words, the story of electronics is the story of the conquest of the electron. How humanity essentially understood the nature of electrons and in a way conquered or maybe controlled the electrons. So as I said this course is not like other courses where we are going very deeply into one area. This is like a story of our department, more sort of a technical story of the department or of this engineering discipline. And in a story, I always prefer to go back to the roots. I always prefer to go back to the history, how all this started. And the history of electronics is generally, so that's what we will see now. We'll see what is the history of our discipline. We have seen the state of the art. We have seen how things are happening recently. But the history of electronics can be broadly categorized in three areas. One is the pre-electronics era. So it was the time when before 20th century, when electronics was almost non-existent in common man's life. The only thing that we had was electricity, magnetism, and some rudimentary technologies based on electricity and magnetism. That is known as the pre-electronics era, that is before the 20th century. 20th century is essentially the starting point of the electronics revolution in a way. And it started with vacuum tube electronics. You might have read about vacuum tube diodes, vacuum tube triodes in your school or during preparation. That is the time when this discipline actually started. The discipline of electronics started. Before that, we had, I would say, electrical engineering. If we think in terms of branches at IIT Roorkee, with vacuum tube electronics started the time of electronics and communication engineering. This happened in in the beginning of 20th century, 1904, around that time. And this was a huge invention, I would say. And in this, you might have some knowledge about it, that in vacuum tube diodes or triodes, we have an emitter of electrons. There is there is an emitter of electrons. There is a metal rod which is heated, and on heating the metal, it emits electrons. And then there is another metal rod, and if we apply a voltage on this second metal rod, it attracts the electron on its towards it, and that's how the electrons flow happens in the diode or triode. So by changing the voltage on the second electrode, we can sort of control the flow of the electron. We can have more flow or less flow depending on the amount of voltage that we apply on the other electrode in the vacuum tube, a diode or triode. In triode, in addition to these two electrodes, we have a third electrode which is in between, that is also known as gate. And by changing voltage on gate, we can, again, that gives us an additional freedom to control the flow. So essentially in electronics, in our discipline, in electronics engineering, we want electrons to flow in a controlled manner. And the devices that achieve that, the devices that achieve a controlled, a systematic and controlled flow of electrons, they are the building blocks of electronics engineering. And the first such device was a vacuum diode and then vacuum triodes. By using these kind of device, even transistor is like that. Transistor also has three terminals, and the current between the two terminals can be controlled using the third terminal. So that is essentially also a controlled flow of electrons between the two terminals, between two desired points. So diodes, vacuum tube diodes and triodes in early 20th century facilitated the birth of the electronics engineering, and even computers were made using vacuum tubes in early 20th century. Okay, but this was huge because vacuum tubes are a few centimeter or at least few millimeter tubes, and if we had to make a good decent computer, we had to use thousands of tubes, and that means that we had to put tubes in a large hall. And that was essentially the size of a very large hall, around 100 meters square was the size of vacuum tube based computer. Okay, and then with the invention of transistors, with the invention of solid state transistor, I would say, because vacuum tube triode is also kind of a transistor. It's also a variant of the transistor. We can also say that it also functions like a transistor. The real progress started with the invention of the solid state transistor. In solid state transistor, and this happened in 1947, although the idea was there since 1920s or so, but it could not be invented until 1947 when the first transistor was demonstrated in Bell Lab. And after that, the transistors could be made on a very small area actually, because we just had to put various materials. We had to make junctions of various materials, and by making good junctions, we could make a transistor. And that's when this transistor era started, and that is in late 1940s. And even individual transistors were not so efficient, I would say. In 1960s and then in 1970s, when multiple such transistors could be integrated on a single chip, we could make multiple transistors and achieve a desired functionality from those transistors on a single wafer. Essentially, the integrated circuits. That essentially is the starting point of the modern electronics devices, because after that time only modern uh, telephones or the telephones that used to exist before, they could be made smaller, computers could be made smaller, and this electronics revolution actually started with that. So the first electronics, in a way, first electronics revolution happened with the uh, invention of the vacuum tube electronics. But the modern day electronics is based on the transistor era, and especially after the uh, invention of the integrated circuits, ICs. So that is a sort of history of our discipline very briefly. Before 20th century, there used to be a pre-electronics era. Nothing not much electronic devices existed. Only some electrical devices that used electricity and magnetism uh, were there. But it doesn't mean that that electronics is entirely 20th century phenomenon. Actually, the science of electronics, the physics and the mathematical formulation was done in the pre-electronics era. It was done by the founding fathers. I would say the founding fathers of the uh, of 18th, 19th centuries. Okay, so if we need to understand, or if we need to know the history of electronics, we also need to have a look at the pre-electronics era, what happened in pre-electronics era, and then how that knowledge finally gave rise to the vacuum tube invention and finally the transistor invention. Also, even in current times, it seems that the transistors, although we can achieve huge functionalities using multiple transistors, but it seems that we need to see or we need to make an alternative technology to the solid state transistors, because as I said, because of the saturation in the Moore's law, this transistor era is also saturating. Okay, so let's quickly have a look at the pre-electronics era, just to sort of, for the general knowledge point of view. It is not technically important to know this, but knowing uh, the identity, the roots of a field, in my opinion, is a good practice. It is always good to know about at least our own discipline from the very basics. Yeah, so there is a question from Aniket. What is vacuum tube diode and how they are different from solid state diodes? Yeah, so this is a good question, and I tried to explain this to you in a qualitative way. Although I will explain this with figures maybe in the next class or so. But let me quickly tell you that a vacuum tube diode has two electrodes. That's why it is known as diodes. Diode means di-electrodes, two electrodes, and these two electrodes are sitting in vacuum tube, in a glass tube, and inside the glass tube there is a vacuum. One of the diodes is connected to a heating terminal, and using the heating terminal, that diode is heated. On being heated, that diode emits electrons. I will show you the figure in next class. I have that in my slides. But since you asked, I'm telling this, once the electrons are getting emitted from one of the diodes, they will naturally travel. And if there is a positive potential on the second electrode, this electrode will attract these electrons. And if there is a negative potential, negative voltage applied to that second electrode, it will repel the electrons. So depending on the voltage on the second electrode, the electrons flow is governed inside this vacuum tube. Okay, and that is a vacuum tube diode. In solid state diode, we just have two materials put close to each other, a junction of two materials, two semiconductors maybe, or two types of semiconductors, N-type semiconductor, P-type semiconductor, and that's a solid state diode. So that is essentially the qualitative difference, I would say. Uh, any any more questions? So this is a broad categorization of history of electronics in pre-electronics era, which is essentially the time before 20th century. Let's see how this story started, how this understanding of electrons, understanding of electricity and magnetism started. So the roots actually go back to 1000 BC, around 3000 years ago. And generally, most of the history, most of the scientific inventions are traced back to the Greek history. And the reason for that is that the Greek history is well preserved. It is the documents of Greek history are still preserved. Uh, that's why most of the uh, history or most of the things are traced back to the Greek history. Although various different civilizations also had good amount of scientific understanding, scientific knowledge, but since their texts, their knowledge is not preserved, that's why there is no mention of, or mostly there is no mention of other civilizations. That's why only the Greek civilization is, name of the Greek civilization is mentioned. So the same thing happens here, even about electrons. Around 1000 BC, uh, uh, an unknown Greek, it is said that an unknown Greek observed that when a piece of cloth was rubbed uh, over an amber means uh, there is a fluid-like substance coming from the trees, and that substance then solidifies. So when the cloth was rubbed over that substance, the cloth used to attract hairs or even weed shafts, feathers. So uh, this was sort of an unknown force with which this cloth attracted hairs, feathers, or weed shafts, light particles of remnants of the wheat plant. Okay, so this is the first incidence of observation of this unknown force, this force because of the, and nowadays all of us know that this is because of the charge, because on rubbing two materials, generally we produce electronic charges, and that produces an electrical force. Okay. So that was around 3000 years ago. In 600 BC, the second documented part. So this 1000 BC is the observation of electrical force, electricity, so to say. In around 600 BC, again a small town named Magnesia. The name of the town was Magnesia. It is currently in Turkey, but at that time it was in Greece, Greek Empire. And a farmer observed that a rock uh, lodestone invisibly attracts the iron. So we know that there are magnetic rocks in the nature, and so this is around 2600 years ago. This observation of magnetic force was documented in this town in Greece. So when this rock piece attracted iron uh, tools essentially, and that's how the name magnet came about, from this the name of the town Magnesia. The name electron, actually electron, ELEKTRON, electron is another, uh, or maybe it used to be a Greek word for amber, for tree glue, or for the resins that come out of the tree, and that's how the name electron came about. And similarly, the name magnet or magnetic force came about from the name of the town where it was first documented. Although it, as I told, that people in other areas of the world, people in other civilizations might have also observed these things, maybe even before them. But those things are not documented, and those things are not popularized as they are. So that's why the science history is written like this. Then it is now well known that in around 220 BCE, which is around 2200 years ago, Chinese used a compass-like tool. They used to make a tool which would orient towards the north-south direction of the geomagnetic field. So as you can see, even Chinese even had this tool in 220 BCE, which means that they might have also observed uh, magnetic field or even electric field before, or even Indians could have, uh, because Indians also used to have navigation techniques in those times, and they also used to have compass. But it is, since it is not properly documented, so it is not well known in the world. Okay. So this uh, invention of this Chinese compass, this went to Europe in around 1000 AD, around 1200 years after it was used in China. It used to be, so it used to be there in China, or maybe even in India in BCE times, but in 1000 AD it went to Europe through invaders and traders, and that's how this came into limelight, and that's how, and after that the compass was modified, and it was further uh, used in navigating the seas, and that's how the sea navigation actually started, and that's how even eventually the colonization happened. So this compass invention is considered to be one of the four greatest inventions of ancient China. So you might be aware that in ancient China, paper technology, there used to be paper-like structure. They used to make papers to write things. Printmaking and gunpowder was invented in ancient China. I would say that in last few years, last few decades, the Chinese people or the Chinese state have uh, sort of made their history more accessible, more visible to the entire world. So they have established that these technologies were there in ancient China, and now everybody says that they were made by China. Similar kind of efforts have not been done by Indian uh, side actually. So that's why the in ancient the various scientific inventions, scientific techniques and tools of ancient India are still not properly known to the world. Generally, the science history is dominated by the history of science in Europe, and science in Europe actually flourished more since 15th century, and that is also the time when the Constantinople fall fell down to Ottoman Empire actually. So it was in 1453 when the Roman Empire, the Western Roman Empire, the Byzantine Empire fell down to Ottoman Empire, and that is also the time when the Renaissance started in Europe around that time, and that is also the time when the scientific revolution started in Western Europe. And most of the documented history of science is from that time onwards. Okay, so it is also the time when this idea of scientific method was given. This was around 15th to 16th century, and in the scientific method, it is said that if you have a scientific hypothesis, you should be able to make a model of that to prove that hypothesis, and that experiment should be repeatable and replicable at all the places. Okay, so with that, actual the science started in Western Europe, and most of the documentation is after that period of time. So in 1600s, in late 15th century, late 16th century, uh, this British scientist William Gilbert was the first one, who is also generally known as the first experimentalist, first experimental physicist, that he published 6 volumes about the magnet and the nature of the magnetic force. So it is the first, I would say, uh, detailed study of the magnet. And he also, and it's not that all of his observations were right, some of his observations were wrong. He published observations about electric and magnetic, both electric and magnetic field. Then in 1660s, uh, Otto von Guericke in Germany essentially produced static charge by rubbing a piece of cloth over a sulfur bomb. So it is pretty much like the charge that was produced by the Greek 3000 years ago, but now since a sulfur ball was used, the amount of charge was more, and the charge could be sustained for longer time. But he didn't know what to do with this, but he sort of gave a method of generating and storing the static charge. Then in 18th century, 1729, uh, Stephen Gray studied the conductivity of various materials, how the charge conducts across various materials. He established, or he sort of observed, that all the materials do not conduct electricity at the same pace. So that was also an important step. In 1733, Charles Dufay discovered the polarity. He discovered that there are 2 kinds of charges. One is positive, one is same type of charges repel, opposite charges attract. So that's when the polarity of electrical charges was discovered. Okay. Then this is just a story, I would say. So please don't worry too much about these timelines, because this will not be there in your exam. This is just for our understanding of the foundations of the field. In 1745, again, it was in Netherlands, and as I told you that most of this history is the history of Western Europe, because that is more well documented, and after Renaissance, scientific things happened there at a greater pace. But it's not that things did not happen at other places. It happened, but it was not properly documented and attributed. uh, then in United States in during 1706 to 1790, Benjamin Franklin was actually a polymath. He was a politician as well as a scientist. He actually invented the lightning rod. He was studying the natural lightning, and at that time, it used to happen that the lightning, the thunder lightning, used to strike churches quite frequently. But people didn't understand what was the reason for that. They used to think that it is some kind of divine uh, uh, intervention or punishment from the divine. But the reason for that was, generally the churches used to have these iron structures or iron top, and they used to attract this thunderstorm or this lightning uh, there, and that's what Benjamin Franklin studied in late 18th century. And there is an interesting experiment that he conducted. I would suggest all of you to go back and maybe go through the experiments that he did. He published his results. Then Coulomb came and he gave the Coulomb's law of electrostatics. So basically, in 1789, Coulomb put everything together in the form of mathematical formulation, and that was the first mathematical formulation of the electricity and magnetism. That was Coulomb was more focused on electrostatics, but he was the first one to use equations to formalize things. Okay. So I guess it is already, we are already overshooting the time. So maybe I will stop here at the Coulomb and we will quickly finish this history part and begin the introduction of semiconductor devices in the next class. So in the meantime, I would request you to figure out a 1 hour slot that I can use whenever necessary. And I will also share with you the link to submit your meet and greet videos. Do you have any questions or anything that you want to share?
So will you upload this PPT on the files?
Yes, I'll upload all the PPTs on MS Teams file section.
Sir,
Anything else?
sir, is
Yeah.
the size of the transistor reduced to increase the efficiency of the transistor, or just to cover more transistors on a specific area?
So definitely to put more transistors in the same area. Second is second motivation to reduce the size is to increase the speed. So the time that the electron takes to go from one terminal to another terminal in a large transistor is more, and in small transistor is less. Okay, so to increase the speed of the transistor, to increase the transit time of the electrons through the device, the transistors uh, are made smaller. So that is another factor. Third is obviously with more transistor we can make uh, or we have freedom to make more logic or more algorithms on the same chip. So that essentially depends on the number of transistors. Yeah, that's essentially what it is.
So, sir, from this we can conclude that a smaller transistor is more efficient than a bigger one, like individual one I'm asking about.
Sorry, your voice was breaking. Can you please repeat your question?
Sir, I'm asking like a smaller individual transistor is more efficient than a bigger individual transistor.
So Ayush, actually, you are talking about efficiency, but but what is efficiency in your understanding? If you think that the speed is efficiency, then yes, it is increasing. But at the same time, there are certain things that are adversely or that are uh, now not good, because on the same area of the chip, if we have more number of transistors, the power or the power dissipation, the heat is increasing, and that is not good, because if the heat becomes above a certain point, that will adversely affect the transistors in return. So
Actually, I meant a speed factor.
yes, speed definitely, speed definitely.
So
Yeah,
the
speed increases.
decreasing the size of transistors means decreasing the power dissipation also.
Uh, yeah, so the power dissipation also, in addition to size, the power dissipation also depends on the voltage levels that we use in our devices. So once you do your advanced courses, you'll see that the power dissipation actually depends on the Fermi levels of the contacts in the transistors. So this idea of Fermi level might be new for you, and that depends on the voltage levels that we use in our devices. So size is a factor, but in addition to that, there are more factors which affect the power dissipation. On an individual transistor, the power dissipation uh, might get might be small, might be low, but when we see the power dissipation on the same chip, it will increase because the number of transistors is increasing.
So does a small transistor get overheated more easily than a bigger transistor?
Uh, as I told, that is not the case always. That depends on the voltage levels that we use in a small transistor and depends on the application as well. A small transistor has a disadvantage of having a small surface area, and the small surface area means that it can dissipate less heat actually. So that way, it even if the amount of heat that is being produced is less than a big transistor, the amount of heat that it dissipates in the environment is less as well. So that's how it is. It is sort of a trade-off and a balance between the heat that is produced. In a small transistor, the heat that is produced is definitely less, but the heat that it can release to the environment is also less, and that way it, in some cases, this might get heated more than a big transistor. But if the surface area is properly optimized in the transistor, so the transistor is a 3D structure, and there are multiple possibilities in which a transistor can be fabricated. So if the surface area is properly uh, uh, designed, in that case, this heat dissipation can also be tackled to an extent. Yes, does it answer your question?
Yes, sir. Thank you, sir.
Yeah, any other questions? If not, let's close the class, and the next class is on Monday, so I'll see you on Monday. In the meantime, if you decide about your CR, please let me know, and if there is any other question, you can also write to me. Okay.
Okay, sir.
Yeah. Okay.
Thank you, sir.
Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.